Welcome to the third day of the macOS and iOS Security Internals Advent Calendar. Today we will look at the topic of PAC, the pointer authentication codes that Apple uses for a while, and let's dig into it. So PAC, or pointer authentication codes, is basically a new security mitigation at hardware level. It's basically a supported feature of ARM version 8.3, and all recent iDevices and the Apple M CPU line, they all support this feature. However, the Apple implementation is slightly different from what ARM originally designed. So there's a bunch of stuff that is not really actually documented because it's Apple proprietary. So what exactly is PAC? The basic idea of PAC is that when you look at a pointer in 64-bit world of ARM64, you will notice that, first of all, by standard, the physical address space is not 64-bit. So that means within a pointer, there's always a number of bits that is practically unused by architecture. But furthermore, it's actually possible to specify in the configuration of the system by tweaking system registers. You can configure how big the virtual address size actually is. And so that means when you reconfigure the virtual address space size, it basically means that only the lower part here is really used for the address. And this part in between here, and also this part here, they're practically unused. Of course, you have usually values like FFF or 000 in it, but they're not really required to address the target object because it is obvious what they're supposed to be. So that means it's kind of something that can be used by different features. So, and now this is where PAC comes into play. The idea is that we use the unused bits to store a code, basically something like a hash, inside each pointer, inside the unused bits. So as you can see here, we have this kind of setup here. We have the original pointer that we want to protect. We have a so-called context. In the terms of cryptography, you can see this is like the maybe the initialization vector. And then you have a key, a crypto key. And all of these three things together go into an algorithm that is called P here. And the purpose of the algorithm is basically to spit out a PAC code. And this PAC code can then be embedded into the unused bits of a pointer. So the thing here is that depending on the context, the pointer and the key, if you change only one of them, of course the PAC code will be different, and that's the whole idea. So when you modify the pointer, the generated PAC code will not match the stored one. So what about this algorithm P? So originally, when ARM designed this PAC feature, they designed an algorithm called Qama that supposedly creates the PAC code from these three elements here. The issue here is that Apple does not seem to use Qama, and what algorithm they use is basically unknown. And it's a black box that we have no clue what it is. So only people inside Apple will know what the algorithm actually is. Or maybe it is Qama, but tweaked in a way. So to make this here work, what we need, of course, is support by the CPU for it. Also, we need to ensure that actually code makes use of this new feature. Because this feature is something that you cannot just add transparently to the system. So that means you need actually new instructions in the CPU that make use of these specific pointers. So we need to have new so-called PAC instructions. The other thing is we need to have the back configuration registers to ensure that we can store the keys and so on. And so the idea here is that there's new system registers in the system to store the different kind of keys. So now let's say we have calculated the pack. Now we can revisit our pointer with the unused bits. So inside the memory configuration, you can ensure if a pointer is actually so-called tagged or not. So when the pointer is tagged, then the upper byte here is basically used for the memory tagging. And in this case, this is kind of used by the system already. So that means that the unused bits of the pointer are basically these between the configurable virtual address size up to here. So that is a minimum of 7 bits, but in reality in iOS and macOS, they use less bits for the virtual address space. So it's actually possible to use more bits in macOS and iOS depending on the configuration of the CPU for the pack code. And as you can see now, the pack code is now in the middle of the pointer. So when you look at the pointer, it will no longer look like a normal pointer. It will look like a little bit gibberish in the middle, especially maybe for kernel pointers, where we use that all of this here is FFFFF. But now there will be like a value in there. The thing is now that the CPU will detect if you flip a bit in the pack or if you flip a bit in the pointer, because then these two elements will not match together. However, what you also need to remember is this is not an encryption of the pointer. So that means the lower part here will not be touched at all. That means if you leak a pointer, you still know exactly where in the address space you are. It is simply that this part here is a hash that we cannot basically easily calculate. So in some cases, when memory tagging, for example, is deactivated, it means that this area in a pointer is also not used. And in this case, this part and this part together can be used to store the hash value. So the more bits you have in the hash value, of course, the harder it gets to just randomly guess the right value. Imagine here, when you have only 7 bits, it's basically a 1 in 128 guess to be able to guess the right pack value. So in theory, in such a setup, you could basically just guess a pointer, and 1 in 128 cases you would guess correctly. And depending on what kind of context you are attacking, this could already be something that is brute forceable. Yeah, so the more bits, the harder to guess it, basically. Also keep in mind the 15 bits is here the minimum. The real virtual address size is actually smaller, so that means we have actually more bits available in macOS and iOS. Okay, so that was the basic idea of where the pack code gets stored in. Now, as I said earlier, we need actually new system registers to store the keys that exist. And by default, ARM version 8.3 defines 5 keys. They define the so-called IA key, the IB key. These are for I, which is instructions. So these are 2 keys for usage on instruction pointers, like function pointers and so on. And then you have 2 data pointer keys. We have the DA and the DB key. And that means we have, again, 2 different keys to protect 2 different kinds of data pointers. And then there's this GA, the generic A key, which can be used for generic stuff. So as you can see here, for each of the keys, there are 2 system registers. And the reason for this is that the system registers are 64-bit wide, but the key is 128 bits wide. Yes, again, this kind of stuff here is the original functionality from ARM. And how this works in Apple is always a little bit questionable because they actually have a non-standard implementation. So, as I said earlier, in order to make all of this work, you need to have support from the instruction set, because this is a feature that cannot be transparently added to your code. So your code must use explicitly these pack instructions. And here is a list of the different kinds of classes of instructions that were added to the instruction set. The first one here is loads that are directly loading from a pointer that is having a pack code. If you would use a normal load instruction and give it a pack protected pointer, it would try to access a memory area that does not exist. But with this kind of class of instructions, it will know that this is a protected pointer and will automatically basically make the access to the real and address in case the pack matches. If the pack is incorrect, this will actually not work and access an inaccessible address, and this will cause an exception. Then there's the class of out instructions. Those are basically taking a pack pointer and checking if the pack is correct, and that's it. Then we have the branch instructions that only branch if the pointer is correctly pack protected. Again, otherwise it will branch to a wrong address and it will cause an exception. We have the same thing for exception returns and for normal function returns. So in all of these cases, the target address must be protected. If it's not, it will return to the wrong address, and this will of course cause an exception. When you deal with pack pointers, the question is, how can you turn a normal pointer into a protected one? So this is where the class of pack instructions exists for. If you have a plain text pointer, you can then run any of the pack instructions to basically add a pointer based on a specific key and a specific context, and then your pointer is protected afterwards. And there's also the class of xpack instruction that basically does the opposite. It removes the protection from the pointer. So let's have a look how this is actually used. So here's an example from, I think, Qualcomm, how you could use this to add a transparent protection of function prologues and epilogues. What we have here first is a pack instruction that is an alias for a different kind of longer instruction. But this alias here basically says, take the instruction A key, protect the current stack pointer, and because it's an alias, it is actually protecting the x30 register, so the return address. So it's protecting the return address with the A key and using the stack pointer as the context. Remember, the context is kind of the initialization vector. The idea is then that this x30 is protected after here. It will be stored on the stack like a normal return address, but it's not a normal return address anymore. It has a pack code now inside. That means when it's later read from the stack, it is protected, which means it cannot directly be used as a return. So it first needs to be authenticated and the pack must be stripped. And this is where the out instruction comes into play. It does the same thing in reverse. It authenticates the pointer with the IA key and using the stack pointer as the context. So what does it mean? It basically means that while it's stored on the stack, it is protected once by the IA key, which is unknown. And second, it's protected by the stack pointer, as a context. This means if you would steal this specific value from the stack and maybe make it appear in a different stack frame, it will no longer work because the stack pointer in a different stack frame would be different, and so the context would be different, and so the decoding would not work because it's not on the same depth of the stack. However, if you had the same depth of the stack and you would be able to steal it, you could make the code flow to a different return address, but only if it would be at the same depth of the stack, and if you could steal and use it later in an override. So how is this now used in macOS and iOS? First of all, let's have a look at the source code level. At the source code level, Apple created a header file called pointeroutz.h, which is coming with the SDK on macOS and iOS. And it's also part of the source code of the kernel and so on and so on. And the idea is to provide basically an API at C level for dealing with pack codes. So to make it as transparent as possible, so it's actually using a lot of macros. Test, test, test. Now we can have a look at the pointeroutz.h file. As you can see here, they define a number of enums first. So they've defined, for example, the 4 different kinds of key, the IA, IB, DA, DB key. And then they have a lot of aliases for these keys. For example, they have the pointeroutz key process independent, and this is the IA key. They have the process dependent code, which is the IB key. The process independent data DA and process dependent data DB. And then they have stuff like a function pointer is process independent, return address is process dependent, frame pointer is process dependent data, and so on and so on and so on. Actually, not so much more. They have a key block function as A, and VXX table pointers is DA. So this is what they define first, and then they have all these built-in functions like pointeroutz strip, which removes the protection, blending and discriminator. They have apply here for protecting a function pointer with a discriminator, and so on and so on. So for all the different kind of usage, they have a built-in function, and they have a macro for using this in your own code. And yeah, that's basically how you use the protection. You basically just use the macros here, and then your code will automatically be protected with pack. So let's look at a real-world example of how this is used. Here we see code from libmalloc. Libmalloc is basically the basic malloc implementation in userland that all normal code uses. And as you can see here in one of the libmalloc header files, it specifies a number of defines, like a malloc zone function pointer, a malloc introspect function pointer, a malloc introspect table pointer. And you can see it defines different kind of pointeroutz macros. It tells here, okay, this here is using a process independent code. So this function pointer is protected with a key that is process independent. Here's the same thing, and this here is independent data. So this here is a function pointer table, and this is the actual function pointer. What you can also see here, it's using a so-called string discriminator to protect the pointer. As you can see later on in the binary, this is actually the context that is used. Yeah, so this is the first part for the setup. And the second part is then in the structure that is used. You can see here, we're defining here the type of the malloc zone structure. And in the beginning of this structure, we basically have a bunch of function pointers to all the different malloc functionality, like size, malloc, calloc, valloc, free, realloc, and destroy, and it actually continues here. And as you can see here, all the function pointers are basically defined as malloc zone function pointer. So automatically they get their pack modifiers applied to it, so that when you use them in the code, the compiler will automatically generate pack protected code for the specific access. Yes. So now let's have a look at how this looks in binary land. So as we can see here, this is also from inside libmalloc as a compiled version, and this is from iOS. What we can see here is that it uses packebsp, which is basically protecting the return address with the stack pointer as context and using the IB key for the protection. Yes, so this is exactly the same that I mentioned earlier, just that this time we use the IB key. What's also different here is that it uses one of the new instructions to directly return to the protected pointer. Again, if this pointer is modified, it will actually cause an exception. But the point here is this is the direct code. In the example from Qualcomm, you could actually see that they first do an out and then a normal return, but this here is basically doing this automatically at the same time. So when it comes to library functions, it's a little bit different. As you can see here, this is the Objective-C retain function that is called from our code. And here you can see that it's reading the retain pointer, it's loading it, and then it's branching to it using the position of the pointer as context, because for BRAA instruction, this here is the pack protected pointer, and this is the context, and the context is basically the address of the pointer. This is something that Apple uses in all the cases. They usually have the address of a pointer as the context. So this here uses the IA key, and when it comes to the IA key, they are actually shared among certain processes, so they can be used for inter-process attacks. There's a file called pack.md, which I will go into later, which that basically discusses this in close detail. The code you can see here is also from libmalloc, and what we can see here is that it takes the malloc zones pointer, it dereferences it, and then it reads a function pointer from inside the malloc zone, and then basically authenticates this pointer. So that's basically the address of a data pointer. What we can see here is that it uses x8 as the context. x8 is partially the address of the zone pointer, and the other part is basically overwritten. Stop. Okay. Let's have a look now at this code example here. As you can see, this is also from libmalloc. And what we can see here is that it references the malloc zones pointer, it reads it, and then it reads the pointer at offset 60 hex inside the malloc zone structure. This is a data pointer. It's basically a function table to function pointers. And what we can see here is that it protects this function pointer table with pack, and it authenticates this pointer with a context. And the context here is basically a fixed magic 16-bit value. So the data is basically protected with a fixed, well-known context. The security here comes basically from the fact that we don't know what the data A key is. So once it's read this and authenticated this pointer, it will then read inside this function pointer table. It reads at offset 8 and then branches to this function and uses x16 as the context. So what is x16? First of all, when you look at this instruction here, you will see that x16 is actually the address of the function pointer that we are reading. So it means that the context once again is the address of the pointer that we are calling. But when you look at the code in between here, you can see that the upper 16-bit of this context are overwritten with this magic 16-bit value. And this is exactly what you can see here in the code. Usually when it comes to function pointers, Apple basically defines the context as the modifier shifted by 48 bits, and the lower bits are the actual address of the pointer itself. So the big question, of course, is also what is this modifier, because we see hard-coded values here. And because that's the big question mark, I actually set out to find out what this is. And as you can see here, when you look at the code, the 16-bit modifiers actually come from this built-in of the compiler, which is pointer aus string discriminator. And in this case, the string discriminator is malloc introspect table. So, but what are these values? Where do they come from? So, as I said, this is a built-in for the C compiler, a built-in from LLVM, and I tried to basically reverse engineer CLang to figure out what this is. So the easiest way to do that I found was to reverse the lib CLang. And I tried to find this pointer aus string discriminator. And the easiest thing that I found was basically that there's a function called CLang get pointer aus string discriminator. So from this kind of name, it seems to be quite obvious that these are basically related to each other. And then I reversed this function and I figured out that the code basically comes down to calling zip hash 2,4 on the string, doing a modulo fffff and adding a 1 to the result. So if you know what zip hash is, you would know that zip hash is actually a keyed hashing function. But as you can see from the code here, there's actually no key provided. And the reason for this is that the Apple implementation of this zip hash 2,4 has a hard-coded built-in key. And from reversing, I found out that this here is basically the hard-coded key that Apple uses. And now, if you take like an open source zip hash 2,4 implementation from the internet, and you use this key here, you will be able to basically calculate the modifier values. So here again, we have our example from libmalloc. We have here our zone introspect. We can see this here is the magic value. And when we run our open source zip hash with the built-in key and use the malloc introspect table, we will see that this is the same value. So that is basically how these magic modifiers come. The good thing about these magic modifiers is that because they are derived from actual strings, they will not change across versions normally. So that means they're quite handy for reversing code because they basically give away the string that was used to derive them from. And this can help a lot for especially more crazy object-oriented code, because you can figure out what functions were called inside a function table, or let's say a method table of objects, basically. Okay, so much for that. Now let's get back to Apple and their weird documentation of their implementation. So Apple has this very nice documented way how they use pointer authentication. It's all written down in a document called pack.md. In this, they document a lot of things, like especially how the A keys and the B keys are supposed to work. And at some point, Apple actually shipped this pack.md file with the public XGNU source code. And then a version later, they removed it again. And so this is the thing with Apple. Sometimes they release stuff, maybe accidentally, and then they realize that and remove it later on. So it's good to actually have the internet around, because they usually archive everything. So when you look for Apple XGNU pack.md, you will likely find your own copy archived somewhere via Google. Just search for it. So I have looked into this packmd file, and when it comes to the A keys and the B keys, they are actually quite well documented here. So here, for example, it says what's about the A keys. So the A keys are basically derived from a field inside the process structure, the struct task. And so they're basically assigned to it by the shared region that a process uses. And the thing is that they have the idea that different kind of processes use in different shared regions. For example, system processes use a shared region that is across all system processes the same. The only exception here is if there's an entitlement, which is COM Apple Pack Shared Region ID inside the entitlement of the process. So all built-in processes use the same ID, except when this here is defined. So the WebKit renderer and also nowadays the parser of iMessages, they use specific shared region IDs. All the other system processes basically share the same. For other processes, they basically use the shared region depending on who compiled and signed the binaries. So this is depending on the team identifier of the code that you are running. And nowadays, there's also certain internal features like POSIX spawn that allows you to start a process with a specific shared region identifier, so they can also share the code. But the POSIX spawn is something that is privileged anyway, so normally you couldn't do this yourself. But yeah, so basically what the A keys point to is dependent on what shared region is assigned to the process. So the system processes share it, and processes from the same team also share the same. Exceptions are processes with a specific entitlement, and so on. This means that the A keys are actually shared among some processes, but not all. When it comes to the B keys, you will see that the B keys are actually assigned by random at the process starting time. So each process has their own B key, and that's usually used for protecting the stack pointers. And the kernel land also uses the B keys for protecting the kernel stack. But they call this here that there's a kernel key diversifier. So the idea here is that kernel keys are automatically different from userland keys, but this is all, like I said, this is all the non-standard implementation by Apple. Okay, and that's it for today. I hope this gave you a good example of how pack is used in macOS and iOS and what pack is at all. See you back tomorrow.